Okay, so now we want to launch our own rocket to intercept the enemy rocket before it hits its point, which is supposedly a city. Um, so here I'm shooting it basically a straight rocket, like a perfectly straight rocket at the at the ordinary rocket, and I just choose. This is above view right here. This is the XY plane. So right here you have, along this x-axis is the enemy rocket. So I just choose a random location out here for our defense base, basically, and I just chose 35 miles and about 53 degrees from the enemy missile. And so if we recall polar coordinates, we have x equals r cosine theta, or in this case, I guess, phi, and y equals r sine phi. So up here we have our r is 35 for both, and our phi is 53, so our x position is actually 21.064, and our y is 27.952. So now that's our initial position, and of course our z is 0 because the rocket hasn't gone into the air yet. And okay. Okay. This here is the position vector for the enemy rocket, and here it's 0 for y because obviously there's no, and we want the rocket, our defense rocket, to intercept at least 1,000 feet above the town. So I just chose 5 miles because that's plenty of distance. So now I need to solve for z, or how much time it takes for the enemy rocket to hit that that where z is 5 miles in the air. So I take the z component here, and we add 5 to it, and you set up a quadratic formula here to solve, because the z is gonna hit z twice, and so we solve that down here, and you can see that we get, here's our 2 z's, but we're only interested in the later one because we by the time it hits the first z, we haven't even launched our defense rocket yet, so we need to go for the second one. So we go ahead and substitute that new time, 0.0673 hours, into our x component here, and we'll get that the enemy rocket will be at 5 miles above the town when it has traveled 180.123 miles in the x direction.